Oh, we should be live. Welcome to Nonlinear Optics. I'm glad that you made it to here. So now I should also be visible online on YouTube, live on YouTube. Once again, welcome to Nonlinear Optics. I'm glad that we can be here again. So you can. So here's a free seat. So there are actually quite a few free seats available still here in this room. We have, I think, something like 5 or so listeners online. Okay, sorry for that. Yeah, nonlinear optics. Let me start with a few words about the significance of nonlinear optics. And I've prepared a few slides here. So a few slides. So let's see. Optics is the oldest discipline of physics, actually. And the father of optics, this is Ibn al-Haytham. Right, in the Western world known as Alhazen. So he was active in the golden age of Arabic or Islamic culture. So for the Western people here, around the time from Karl der Große, Karl Magna, to 1200 or so, or 1300 or so, where the Islamic world was essentially the most important and actually also the one that influenced the Western world quite a lot. Right? So what you see here is an influential book, or the title page of an influential book that was reprinted for centuries. And so it's Thesaurus Opticus, it's called in its Latin translation. And what it depicts here is Archimedes of Syracuse, who allegedly put the Roman boats on fire by using a parabolic mirror. So probably this never happened, but anyway, it's a heroic tale of optics, right? What you see here is something very remarkable. It's an anatomic study of the human eyes and the nerves. Yeah. So and you know perhaps that that we have this what's called the optic chiasm. Yeah, so this cross-like structure of the nerves. And so Alhazen, 1,000 years ago, he knew about that. Certainly he didn't know the entire function, that's clear, but it's very remarkable. So the scientific revolution that he was responsible for, actually this is not a true picture of him. Yeah, so there is no picture of him. This is just an artist's view of Alhazen. And, well, the scientific revolution that he and others started was that, if you remember what the old Greeks thought about light, they thought that the eye, kind of emits rays, and that we see in this way, where Alhazen had the opposite opinion and the correct opinion, namely that that light from what we see comes into the eyes, and that it's that this is the reason why we see. And his argument, or one of his arguments, is quite interesting. He said that if you look at the stars, then they are very far away, and it would have taken, it doesn't make sense that if we look at them, that we send rays to them, it would take too long. Right? So he obviously already had the idea that light has a final speed, and actually he had a mechanic view of optics. Well, enough on that. let's make a big jump and we go to James Clerk Maxwell. And he in 1865 established this set of equations. Actually, he didn't write it in that way. He wrote down 20 equations. So for each component here, one equation and then a few other equations. It was only later by people like Heaviside, Oliver Heaviside, who put Maxwell's equation. Well, and you see, I write here Maxwell's equation, but you see here there is Gauss' law, there is Faraday's law, there is Ampere's law, and there's the other law which I like to name the no-name law. Yeah? So the only thing that Maxwell actually did kind of was to add this correction to Ampere's law. Yeah? And it took another 20 years or so. In 1886, that Heinrich Hertz made his famous experiments proving or generating radio waves and detecting them, transmitting them in space without material, such that the that this quantity here was proven. So this the displacement current that was invented by Maxwell in order to remove a mathematic inconsistency of Ampere's law. You probably are well aware of that. Second semester, if you had experimental physics with me, then this was one of the highlights actually of such a lecture. Yeah. Well, this is of course not the final word on optics. This was not the final word on optics. The final word is kind of quantum electrodynamics, namely the quantum theory of light. Of course, has nothing to do with what we do here in the framework of nonlinear optics. So this is field theory. But if you're interested in, if you look for a easily accessible introduction to quantum electrodynamics, then I can recommend this book. Say for the Christmas holidays or so. There are hardly any formulas in this book. So he wrote it for the general public. Okay, now let's look what is the core of nonlinear optics. So it starts with this material equation that we wrote down in introductory electrodynamics, namely that the polarization. So you remember the sum of all dipole moments of some piece of something divided by its volume, so that that this polarization we wrote down as in this form here as a susceptibility times the dielectric constant or the electric field constant times the electric field. So the idea is, if I apply an electric field to some material, then some polarization is created. Right? And now if you compare this equation here with Maxwell's equations, then you have to realize that the quality of this equation is very different from the quality of Maxwell's equations. This is just a power series expansion, or the first term in a power series expansion, whereas Maxwell's equations are laws of nature. Right? So I sometimes like to say that Maxwell's equations, they are made by God, and this is made by man. Right? And actually, this is already one of the central points here, or the starting point of this lecture, that we will correct this thing here, that we will introduce also the next terms besides the linear term, also a quadratic, and finally a cubic term. Well, let's look a little bit into the history of nonlinear optics. And, well, in contrast to optics, which goes down back to the Greeks, to the old Greeks, and then later to the Arabs, and then all the way through, well, through the discussion between Newton and others, what the nature of light is. Is it a particle? Is it a wave? Right? Then Maxwell's equations, Hertz discovery. Yeah, so 2,000 years, more than 2,000 years of history of optics, and in contrast, nonlinear optics is quite young. And it perhaps starts with Maria Goeppert-Mayer. So you see here an isotope table. Yeah, so this famous thing where you plot the number of protons against the number of neutrons. Why this? Well, because she received the Nobel Prize for discovering the shell-like structure of the nucleus. But she also did something else. Namely, she put one of the starting points in nonlinear optics in her PhD thesis. The defense was attended by 3 Nobel laureates. Yeah, so imagine that if you would stand there, there sits 3 Nobel laureates and a few other professors. But apparently it was very successful. And in her thesis, she actually calculated the first nonlinear effects, so to say. Well, actually, it was already Einstein who made a remark in his famous paper from 1905, where he discussed, or where he introduced the photon concept in the framework of the discussion of the photoelectric effect. Right? So he said that the photon needs to be larger than the ionization potential. But he also made the remark that maybe 2 photons can work together, right? And then we are at nonlinear optics. So this was Maria Goeppert-Mayer. She married, this was Maria Goeppert actually, right? And then she married somebody who was the name Mayer, who was a scientist from the United States. Mayer later became the president of the American Physical Society, if I'm not mistaken. Nevertheless, so she did this in the late 1920s or early 1930s. But still, nothing happened. Why? Because in order to produce nonlinear effects, you need intense lasers, or you need intense light, I should rather say. You not necessarily need a laser, but of course a laser produces intense light. And so it was the invention of the laser by Theodore Maiman. You see his picture here. He never received a Nobel Prize, because, I guess because some of his competitors who were not very happy that it was Maiman who invented the laser and not themselves, they were influential and apparently also writing letters to Stockholm and so on. Right? So it's amazing that he never got the Nobel Prize. Whom you see here, this is Reinhard Neubert, and he built the first helium neon laser here in this at this place. So Jena was one of the very early places where laser research was done. And this is the helium neon laser that he had built. Right? The laser was invented in 1960, and only a year later or so, they also had lasers here. So they built it on a massive Zeiss machine bed, right, that you see here, and here you see the tube. So this was the first gas laser. Before this gas laser, they had also ruby lasers. already. But when the 50th anniversary of the invention of the laser was celebrated in 2010, we gave an honorary doctorate to Reinhard Neubert, and he gave a very nice lecture. Well, where? Actually in the time-honored lecture hall here in this house. And you see, everybody knows it? Yeah, so our foreign students perhaps not. Yeah, so it's a really beautiful lecture hall. On this black and white photo, you don't see it. But what you see here is a public lecture they gave at on the 3rd of December of 1962, and the lecture hall was packed to the last seat, and they showed quite a number of experiments with this new light source, interferometry, then transmission of information with modulated lasers, and so on and so forth. Yeah? So quite some sophisticated experiments that were presented. Well, 2 years after the invention of the laser, and just a few months after the first realization of ruby lasers and helium neon lasers. This laser that I just have shown was not in the lecture hall, because it was quite delicate. At that time, they didn't use curved mirrors for the laser cavity, but still flat mirrors. I don't quite know the reasons. Dr. Neubert told me at some point, but I've forgotten it again. Perhaps they just were not delivered in time or something like that. And therefore, there was a student sitting upstairs at this laser and panically realigning the laser such that they had a beam, and the beam was directed down to the lecture hall where some professor did the experiments. And everybody hoped that the laser doesn't switch off. So we had lasers, and they were showing, of course, also nonlinear effects, I guess. It was Wolfgang Kaiser at the Bell Labs, yeah, so a German scientist born in Nuremberg, close to the region where I come from, and he was a scientist at the Bell Labs in the US, and there they saw the first. Yeah, so this was in 1961. They saw the first two-photon absorption, right? Where you excite an atom and with a photon that's actually too small for exciting it, right? So famous experiment, one of the first nonlinear optics experiments. Yeah, so Wolfgang Kaiser then went back to Germany. He became professor at the Technical University of Munich, and as you see here, he is now a very old man, but fortunately he is still alive. I met him at 30 years ago when I was a PhD student in Munich, or diploma student, I don't know actually. So now here you see Peter Alden Franken, and he discovered, same year, let's look at the date here. This was actually September. So the question is when things were received, July 21st. And I didn't write down the submission date. That would have been interesting. But anyway, yeah, so pretty much same time, there was the generation of optical harmonics. Right? And the story, how this evolved, is actually also quite interesting. And also the story about this paper, in particular about this point here, marking the second harmonic, is also very interesting. Yeah, I will tell this story when we come really to second harmonic generation. Well, today, nonlinear optics is nothing special. You can even buy it for a few bucks with a green laser pointer, right? So a green laser pointer, I'm afraid that on YouTube you don't see it. Well, I can put it on the, steer it into the camera. So yeah, so now you see it. Well, I remember very well, some 30 years ago, Ted Hensch was giving a talk at the Max Planck Institute of Quantum Optics, where I was also working. And he had a box like this with the first green laser, right, for presenting things, right? And we were just fascinated. Yeah, so I would tell my wife in the evening what I've seen. Yeah, so spectacular was this to have nonlinear optics. Yeah, that you hold it in your hand. And this thing probably costs, well, several thousand Deutschmark at that time, what Hensch had, but he likes to play, and so he had this thing. Maybe he built it himself. But nowadays, yeah, so for less than 10 bucks, you can buy a green laser, which is actually an example of nonlinear optics, because you don't have a green laser diode inside here, in contrast to a usual red laser pointer, where you just have a red laser diode. Quite simple. But there's no such thing like a green laser diode, as far as I'm aware of. What you have rather is an infrared laser diode. And what you do is the same thing as here, that you frequency double the light. Yeah, so you make green light with something like 530 nanometers out of light with 1060 nanometers. Yeah, and this is how it looks like. So the essential parts are the smallest part of this thing here, right? So the biggest part are just stupid batteries. Yeah, so stupid batteries here. Then you have a little bit of electronics, right? Also has nothing to do with optics. Well, it just is there in order to supply the electricity to the laser diode, which sits here, right? And this emits infrared light, as I've said, right? And then you have a lens, and here, this is the only thing that is nonlinear here. Well, of course, you can argue that generating the laser light, well, yeah, so depending, well, I wouldn't call it nonlinear optics. No, definitely not. Yeah, but very clearly, so this here is nonlinear optics, a KDP crystal, and then there are some lenses in order to collimate the beam, right? So a little piece, if you take it apart, I'm afraid you wouldn't find it. Yeah. So this is a diode-pumped solid-state laser pointer. Diode-pumped solid-state laser pointer. Yeah. Now, this is just a course with 2 hours per week and some recitations. But actually, it's just kind of an introduction to nonlinear optics. So if you look at the curriculum that we offer here in optics, in this course, in this master's course of photonics, then you see actually a lot of lectures that, well, where nonlinear optics plays a central role, but you don't find it actually in the title of that lecture. So, and I've just depicted here, so it just looked at the list of lectures that are offered here. And, well, yeah, so, well, some actually say something about nonlinear optical properties of solids, but all those highlighted lectures and probably a few more deal with nonlinear optics. Yeah? And well, for the third semester, the situation is not different. also there quite a few lectures where nonlinear effects play a central role. Yeah, so it's very well worth to look at nonlinear optics and to study it in some detail. Good. Well, this course, what are we going to do? We will start right away with a review of linear optics, just as I did it already a little bit, where I wrote down the polarization, right, and Maxwell's equation. So we will go in the same direction, and we will look at the physics of the refractive index. Now, I'm not sure whether this has been, that you have been exposed to that, but repeating that in order to see from which roots we develop nonlinear optics, and which concepts that we know from linear optics can be recycled in nonlinear optics. For this, we are doing this first chapter. Yeah? So let me then say what is the core or the central thing to be learned here. These are the coupled wave equations, right? And what we are trying to do is to get there as quick as possible, such that we can work with these equations, right? And therefore, after looking at some effect, namely the electro-optic effect that you probably know already, but which can be seen as as an early manifestation of nonlinear optics, we will do a quick overview of nonlinear effects, and then these two chapters, so chapter 4 and 5 in this list, they are, so to say, the core of this course. And then we will look at some examples, so it's some applications of these coupled wave equations, namely some frequency generation, second harmonic generation, so what we have built in here in this laser pointer, and only then we will cover some things that if you just think about a logical sequence could have been developed before. Yeah, so we will, for example, look at some properties of susceptibility. So the concept that we introduced already a few minutes ago, so a more detailed look will only happen then. Same thing with anharmonic oscillators. You will see in a few minutes that when we look at the refractive index, then a good model is the so-called Lorentz model, where we treat the electron, the bound electron, as a harmonic oscillator. And now if you think about nonlinear optics and perhaps also where this name comes from, it's probably not so surprising that we will talk also about an anharmonic oscillator. Yeah? Okay, when all of that is done, then we come to the last part of this course, namely to so-called third-order processes. And the most important there is the intensity dependence of the refractive index, because the intensity dependence of the refractive index has a huge influence on the propagation of light pulses. And if you look around here in this institute, in the optics labs, then you find in almost all the optics labs something like a femtosecond laser, right? And in order to understand the propagation of these pulses, you certainly need linear optics, and there will be a chapter, a supplementary material where I treat this. But of course, the really interesting part, well, the other is also interesting. I shouldn't say it this way, but well, the new part, to say it in neutral words, the new part then will be will be the nonlinear propagation of pulses in media. Well, and if there is time, I would also look at ultra-intense field and high harmonic generation. But experience tells me that it's unlikely that we can have a detailed look at that. But actually, there are specialized lectures on these topics, on these last two topics. Good. So now, let's go back to linear optics. Let's start right away with linear optics. So as I said, we are dealing with the classic curriculum of nonlinear optics. So we are not doing quantum mechanics here. So we don't look at the quantum mechanical background of nonlinear optics. Rather, we look at the classic curriculum of nonlinear optics. Maybe a few words on the organization of this lecture. We will discuss that in a subsequent, so right after this lecture, Matthias Kübel, Dr. Matthias Kübel will come, and then we discuss a few things on how this lecture is organized, besides, so how this course is organized besides the lectures. So now linear optics. We will look at wave propagation in general, but wave propagation in anisotropic media in particular, because anisotropic media play a particular role in nonlinear optics. The reason I can't explain at this point of the lecture, but you have seen that there's a crystal here built in, right? And the crystal, and this is actually an anisotropic crystal, so not a cubic crystal. It's an anisotropic crystal that has different refractive indices depending on the on polarization. So it's a birefringent crystal. They play, as I said, a particular role in nonlinear optics. And this is one of the reasons to look at wave propagation in these crystals. But actually, this first chapter is of much is much more fundamental than just looking at anisotropies in media. In general, I will write things here on this iPad. So you see it here, right? And I will write the important things. I will write on this iPad. Then you would take notes. But I thought that this material, which most of you are probably quite familiar with, that I do this, well, in the mode of that's by PowerPoint, right? So I will do it by PowerPoint in order to be fast. So with PowerPoint you can cover 2.5 times the material as compared to writing it down. Of course, it's clear that at this speed, would be too fast for new material. But as I said, I don't think that some aspects may be new, but in general, I think it's known to you. Okay, so nonlinear optics deals with nonlinearities of the refractive index. In optics, you learn that the refractive index is a material constant. But this is not quite true. If the light intensity, if the electric field of the light field is strong enough, then the refractive index may depend on the electric field. And in order to get access to that, we look at Maxwell's equations, and we see, of course, that we find the electric field, for example, in Faraday's law, whereas we find the D field in Gauss' law, right? And both are linked by the constituent or material equations, which you see here, Right? So the D field is equal to the electric field constant times this dielectric constant of the material under discussion, and the refractive index is just the square root of this dielectric material constant. And nonlinear optics, as I said, starts when the refractive index becomes dependent on the field strength. And well, just in order to get an idea of what you need, you know, of course, that the electrons are responding to the electric field. They are the lightest charged particles, and therefore they can be accelerated the most, and therefore it's these charged particles that do kind of the optics, that talk to the light, right? And now in some material, these electrons are bound to the nucleus, and you can calculate the forces which bind these electrons to the nucleus. And then you would compare this field, this nuclear field, you would compare it with your externally applied field, with the laser field. Right? And if you would use sun as the light field, then you would find that the field strength of sun radiation, of solar radiation, is much, much smaller, many orders of magnitude smaller, even if you focus it as hard as you can. Yeah, so 8 orders of magnitude, I would just guess, smaller than probably even more, smaller than the field strength inside the material. Yeah? And therefore, we usually means, yeah, so just here sitting without any laser, we usually don't see nonlinear effects. Okay, now we want to introduce the susceptibility that I have actually already shown, and to this end we write the D field as the sum of the electric field multiplied with the field constant plus the polarization using this equation that we already have seen. Right? And if we do so if we replace now the polarization here with this expression, then we find this familiar equation that the D field is epsilon 0, the field constant, times 1 plus chi, the susceptibility, times the electric field. And this then means that the dielectric constant, this material constant, is 1 plus the susceptibility. Yeah, so the susceptibility is, so the name of this material constant is very intuitive. So it says susceptibility, or susceptible means just how sensitive is the material to an external electric field. How susceptible is it to an external field? Okay. Good. This is how it looks. Now we want to get an idea of what the refractive index is on a kind of microscopic level, right? And to this end, we start with the Lorentz model, and later we will actually, design the Lorentz model for nonlinear media. So you all know what the refractive index does. Right? So I have here a plane wave, right? Just here propagating from left to right. And now I have a second beam here, but with some glass in between, a piece of glass in between with a certain refractive index. And what will happen is that, well, that the wavelength here is a little bit shorter, right? And therefore there's a phase difference. And so where both waves are perfectly in phase here, they are kind of out of phase here, right? And the question is, how do we explain that? Now, let's discuss the idea, and once we are familiar with the idea, we do the mass. We just translate the idea into mass. So what happens here is that we have an oscillating electric field, right, oscillates 10 to the 15 times per second or so. And this incident, this oscillating electric field of the laser light, this displaces the electrons and atoms a little bit. So it just wiggles the electrons a little bit. And therefore, we have an oscillating polarization. Right? And an oscillation, and this oscillation actually, this is phase shifted with respect to the incident, to the driving force. This is just the same as you heard in the first semester in mechanics with a driven oscillator. Yeah? If the driving frequency is far below the resonance frequency, then the oscillator follows faithfully the external driving force. Once you get into resonance, oscillator and driving field or driving motor, say in this case, are out of phase by 90 degrees. And if you're far beyond resonance frequency, they are out of phase by 180 degrees. Right? Same thing here. Same thing happens in a material. Yeah? Same equations have the same solutions. Okay, well, so we have oscillating charges. They are, of course, accelerated charges, so they emit electromagnetic radiation. Yeah, so you could think about this in a cartoon-like way, like this. Yeah, so there is this incident wave. Part of it is absorbed or is used in order to drive these electrons. Right? The other part goes through, but this part that sets into motion the electrons, well, results in the re-emission of light, yeah, because we have accelerated charges. So these oscillating charges, they also emit light, but it's phase shifted with respect to this. To the original waves. Yeah? And now you add two signs of the same frequency but with different phases, then you get, of course, again a sign with the same frequency but still another phase, right? A phase somehow in between the phases of these two. So it's dead now. That's not good. That's not so nice. So maybe I can convince it to. So let's see whether this. Okay, I guess I have a problem here. So short break. So I hope you can hear me now again. Good. Yeah. So this was the idea. I think I presented. So it's now no longer a laser pointer. It's now just this arrow. But who cares? Yeah? So I hope this is fine for you. So the idea is clear now. Yeah. So let's cast in mathematics. So we have a harmonic oscillator, so we use the differential equation for a harmonic oscillator, of course, for damped harmonic oscillator. And for the field, we write this, so this equation, which is kind of straightforward. Now, let me make a remark on notation, because we will use this kind of agreement on notation all the time. When I put this tilde here, so this snake-like line here, then I mean an electric field with its full time dependence.
Activate the screen from online.
Oh, yeah. Thank you. Good. So we were discussing the differential equation in order to cast in mathematics what we discussed so far, and we have here the inhomogeneous part of this differential equation, namely the external electric field. And I just said that the agreement is that if you see this quantity here, or the polarization, or any other related quantity with this tilde here, with this snake-like line, then it reminds you that what I mean here is the full time dependence of the field, not just the amplitude or something like that. Right? So the amplitude actually would be written without the tilde, and I can write the amplitude even either plain in the usual way, or with the script version. And when I write it in the script version, then I mean explicitly that the amplitude here is real. Otherwise, or most of the time, we work actually with complex amplitudes, because then it's very convenient to discuss the phases of the respective field. But there's one thing to realize, that physical quantities are represented by real numbers. If I write a complex number, then I do this for mathematical convenience, and I have to make up for that. And the way in which we do that is to use the complex conjugate. Yeah? So I can write this real field with complex quantities if I just the complex conjugate, and quite often we just abbreviate the complex conjugate in this way, right? So then we would use here Euler's formula. Everybody remembers Euler's formula? Who doesn't know it? Yeah, so the exponential with a complex argument is cosine time of this complex argument plus I times sinus of this complex argument. This is what we are using here, right? And if we do so, right, then we can very conveniently write everything in complex notation. We just add the complex conjugate, and because we are lazy people, we just write CC instead of this here. Right? And you can check that out, and you get, if you check it, you get even some little reward, namely this fundamental property that the complex conjugate of the E field as a function of the frequency is equal to the field itself at the negative frequency. Good. So we have this differential equation, right? And in order to solve it, it's the best thing to know the solution. And because this sounds so stupid, we call this thing, knowing the solution, we call an Ansatz. If I would need to find a translation for this word, for this German word that made it actually in international literature or mathematical literature, then I would call an Ansatz an educated guess, right? In other words, you know the solution, right? So, so we know, of course, from physics what we expect. We expect something that oscillates, therefore it's called an oscillator, right? And therefore we write down an oscillation. So this would be the position of the electron, right? And what we say is that it wiggles. So this is what this says. And if we plug it in here, then we immediately find this solution here, right? So we find, and we realize, of course, that this is frequency dependent, right? And therefore I write frequency or circular frequency here as an argument. Okay, now we know where the electron sits, right? So what the displacement of the electron is, and therefore we know the dipole moment of this electron bound to a positively charged nucleus. So the dipole moment is E times R, right? And therefore I can write down the polarization. When capital N is the electron density, then the polarization is obviously N times the dipole moment N times E times R, right? And the minus sign just comes from the fact that I use here the elementary charge as a positive number, so nothing particular here. Okay, so you see we have an expression now for the polarization, and now we compare this this expression here to the one with which we started actually, and therefore we can immediately identify the susceptibility. We just got an expression for the susceptibility. Isn't this great? With such a simple idea to get this profound expression, right? So, yeah, one remark. The polarization is proportional to the electric field. In particular, the polarization, trivial but important to remark, the polarization oscillates at the same frequency than the electric field. Therefore, the polarization, so the oscillating polarization, meaning that we have oscillating charges, it oscillates at the same frequency than the incident electric field, and therefore it also emits at the same frequency. Right? Linear optics is kind of boring because you can't create new colors. So people think that optics is colorful. No, it is not. Right? Because you never get more colors out than you put in. This is different in nonlinear optics. But you realize that we had this very simple linear equation, namely that the polarization is epsilon 0 times chi times the electric field, linear. Now, in order to produce new fields, we'll see that we have to take the next expansion, the next term in the Taylor series expansion. And you can imagine that all the nice mathematics that we have for the linear case is gone, right? I have to prepare you for some ugly things, yeah? So it's going to be, mathematically it's going to be ugly. In particular, because I said that we need to deal with anisotropic media. And Yeah, so this will be one of the next points here. This will make it even more ugly. Yeah? So there's a price for everything. Yeah? And the price for the beauty of nonlinear optics is ugly mathematics. Well, actually, there are also nice pieces of mathematics, I should say. And I should take back what I said. Also, for nonlinear effects, solitons are an example, right? Where you have extremely nice mathematical phenomena, I would say. So, polarization and the wave equation. We need to look at polarization. We're talking about anisotropies and anisotropies. So we need to talk about polarization and the wave equation. Well, I don't want to go through this because you know that. We start with Ampere's and Faraday's law and we arrive at the wave equation, the familiar wave equation. And it is done here in the usual way. Did you count how often you did this derivation in your study? Yeah, so probably several dozens of times, right? No? Okay, well, we use the familiar traveling wave as an ansatz, right? And then, of course, we find what's called the dispersion relation. And then we find this expression for the refractive index. Of course, if you look at the very first page of my script, we had this already. Yeah, so nothing new. Okay, boring. We substitute this equation into the dispersion relation, and then we get for the refractive index here this equation, right? And it's worth plotting this. Because what you see is that if omega is smaller than the resonance frequency, then this term here is positive, right? And therefore, the refractive index is a little bit larger than 1, right? So this is what we usually know. Right? The refractive index is larger than 1. However, if your frequency is high, say you use an X-ray beam, actually you don't even need an X-ray beam, but it's particularly well known for an X-ray beam because they're for sure you're beyond all atomic resonances, then this here is smaller than 0, right? And therefore, the refractive index gets smaller than 1. Which means that the phase velocity then is faster than the speed of light, than the vacuum speed of light. And this is used in X-ray optics. But of course, we are here in normal optics, so we are in this region here. Right? If you have several resonances, then of course things get more complicated. You have to expand this model, and you would get things like this here for the dispersion curve. Yeah? So we call this here normal dispersion, and this here anomalous dispersion. Good. So now you see things start to get more involved. What I want, let's start with the following. So previously I wrote down that the D field is epsilon 0 times epsilon r times the electric field, right? If I write it down in the way I did so far, then this means that the D field points in the same direction than the E field. They are just proportional to each other. However, if we have anisotropic media, then the external electric field may be able to pull the electrons in one direction more easily than in another direction. Yeah? And therefore the D field not necessarily points in the same direction as the E field. Yeah? So this is immediately clear if we are talking about anisotropic media. And therefore we need to describe the dielectric, properties not just by a scalar, but by a matrix. Well, actually it's a tensor because it has certain properties concerning transformation. Well, we write it in what is meant here is that it is written in the Einstein sum convention. Now, whenever you see the same index here in such a product, then you have to then you have to realize that what we mean is the sum. Right? So by definition, this here is the sum over J because J appears here twice. Okay, yeah. So you see that this is a 3 times 3 matrix, and what I want to prove now is that the 3 times 3 matrix has a particular property, namely, this is a symmetric tensor, meaning that the component epsilon 1 3 is equal to the component epsilon 3 1, and so on, right? And well, this derivation is not difficult, but a little bit tricky. Yeah, so one probably would not immediately guess that it's. Yeah, so if somebody would ask you to prove it without knowing the trick, then it would probably take you a little bit of time to find it out. At least this would be the case for me. So we do the following. We look at the energy density of the electric field, right? And we derive the derivative, the temporal derivative of that, of the electron, of the energy density of the electric field. And we do it in this way here, just by this equation here, right? This equation familiar from an introductory course of electrodynamics. And then we would derive this quantity here, so this derivative of the energy density, we would derive it in a different way. Yeah? But first let's do it in one way, namely the one that you see here. Yeah? So we want to calculate the derivative of that, right? And what we have to use is the product rule, quite obviously. Right? And you see that I take the derivative of the second, of the field here written in blue. Yeah, so, and I just keep the first one here, and then I do it the other way around. Right? And of course, I have to write these indices in the right order. But then I rename here the indices. Yeah, so these are just indices. In German, we like to say, Namen sind Schall und Rauch. Names are Schall, what's that? Noise and smoke. Yeah, so you could say. Yeah. So names don't mean anything. Yeah. So so I just rename them, and then then we keep this here, and we try to get this quantity here, the derivative of the electric density, in another way. And for this, we think about the Poynting vector. Yeah, so the Poynting vector S, defined as E cross H, which is the power flux per unit area. And now we use Gauss' law, yeah, so the Gauss-Ostrogradsky theorem. And then we get the net power flux into a unit volume as the divergence of S. Yeah? And the electric part of this divergence of S is the same as, yeah, so this is the energy density. Okay, well, we use a vector identity in order to calculate this divergence of S, right? And what we get is this thing here, right? Okay, so this means that this term here has to be the same as this term here, right? And if you look carefully at it, then you find, well, that what we have here is just, well, that this so we have epsilon kj here, and here we have epsilon jk. Yeah? And you can only fulfill this if both are equal, and this means that epsilon jk is a symmetric tensor. Very important quantity, property of this tensor. Well, this means that we can write down the energy density a little bit simpler. Yeah, it has not 9 terms, but just 6. Right? Fairly simple, I say. Right? You see, this is, yeah. I wouldn't call it ugly yet, but things will go worse in terms of mathematics. But we know, of course, that this is the equation of an ellipsoid, yeah? And it lies in space somehow, right? But of course, we can rotate our coordinate system such that the axes of the coordinate system are parallel to the principal axis of this ellipsoid. Yeah? So this is then called the principal axis system. So a special coordinate system that's rotated such that it is nicely aligned to the ellipsoid. Yeah? And in German we call it Hauptachsen. What's called principal axis in German would be Hauptachsen. And well, just to educate you a little bit of German, yes, you international students, I use here the German abbreviation, Hauptachsensystem. Yeah, so it's a literal translation. Okay, and in this Hauptachsensystem, so in this principal axis system, this equation here, yeah, so this matrix equation looks simple, namely like this. Right, so usually when I write x, y, z, then I mean the principal axis system. And when I write 1, 2, 3 for these components as here, then it's in general not a principal axis system. Okay, well, next point is to derive this equation. Yeah? Who knows this equation? Who has heard about this equation before? Sellmeier? No. This is Fresnel's equation. And for what is it good? Fresnel's equation? Yeah, with Fresnel's equation, you can calculate the refractive indices of a birefringent material. Yeah, so if you know the refractive indices in the 3 directions, so of the crystal, then you can calculate the refractive index in any other direction. Yeah? Okay, so let's derive this thing here. Wave propagation in an anisotropic crystal. So we introduce here this vector S, which is a unit vector, goes in the same direction than the wave vector, yeah, but just it's a unit vector, and therefore we have this expression k times refractive index divided by c. Okay, now if we have a monochromatic wave, then the differential operators, you certainly know that they can simply be, so this Nabla operator can simply be replaced by I times k, or if we use this here as I times omega times n divided by c times this unit vector in direction of the wave vector. And a temporal derivative can just be replaced by I times omega. Right? This holds for a monochromatic wave. Yeah? And therefore, Ampere's and Faraday's law for this case just reads like this. Yeah? If this is not familiar to you, then try it out. Yeah? So it's very simple. Elementary mathematics. And when we have this here, then we can derive a few things that you probably are very well aware of. Namely, this here, so this equation here says that D must be perpendicular to S and D must be perpendicular on H. And from this equation, you find that H is perpendicular on S, right? And H is perpendicular on E, right? And, well, this has familiar consequences, at least the first one here. D and H, they are perpendicular on S. So this just says that we have a transversal wave. All electromagnetic, well, at least a plane wave is a transversal wave. And it also says that D, E, and S are perpendicular on H, right? And this is depicted here, right? So we have D, E, and S, all three are perpendicular on H. And now an interesting and intriguing property, namely S does not necessarily go, so capital S, the Poynting vector, the flux, the energy flux in general goes in a different direction than the wave. Yeah? And of course this has consequences, but we're not interested in these right now. Okay, so we have these two equations from the previous page, right? So this is, so this here is kind of Faraday's law, and this here is Ampere's law, right? And what we do now is that we substitute this one into this one here. So we eliminate H. And if we do so, then we immediately get this equation here. Right, so we have now S cross E equals or is proportional to D. Or if we move these constants to the other side, then we get this equation 49. And then we use again the Buck-Cup rule, the same rule that you would use in order to derive the wave equation from Faraday's and Ampere's law. But here it's a little bit simpler because we have here this term S times S, which is of course equal to 1, right? And what we then have is that D, so we solve here for D, the D is equal to, well, to this expression. Looks a little bit ugly, but, well, fair enough. And now we go to the Hauptachsensystem, to the principal axis system, because in the principal axis system, we can write it in this way. In the principal axis system, remember, D, so this tensor here is diagonal in the principal axis system. Therefore, we can write it in this way, right? And so let's just look here at the x component without loss of generality. You can write down the same for the y and the z component. Right? So we write the same, we write this equation 50 for this component x in the principal axis system, and we find, so we just write this down, right? And then we solve this equation for dx, right? So we have dx here and we have it here, and after a few simple steps, so we find for dx this equation here. So now a trick. So we remember that S is perpendicular to D, and if you write this in, this means that the scalar product of S and D is equal to 0, right? And this is what's written down here. And now we substitute this expression here for dx. We write the same thing for the y component and for the z component, and we get this equation, right? This is Fresnel's equation. This is the equation which we started with. If you think about it, looks a little bit complicated, but actually, it is not really complicated. And so it's actually quite straightforward if you know what to do. Yeah? Well, but of course, this is true for most of the complicated things, all right? If you know how to do it, then it's trivial. Okay, Fresnel's equation valid in the Hauptachsensystem, the principal axis system. Yeah? For what is it good? I mentioned that already. It is good for, now it got a frame here. So what did I write here actually? Oh. Yeah, so suppose we have a crystal in space and we have an electromagnetic wave with unit wave vector S in the crystal, then it's certainly an interesting question how big the refractive index would be, right? So we may know the refractive indices, or we should know the refractive index of a given crystal, but because it's anisotropic, and if we are not parallel with our polarization or beam direction or whatsoever with one of the principal axis system, then we don't know the refractive index, right? And in order to derive it, one would use Fresnel's equation. Yeah? So now you see that this is a quadratic equation, actually quadratic in n squared. So this means that there are actually 4 solutions. One pair of them is just the positive and the negative. So there are 2 physically meaningful solutions. Yeah? So I said Fresnel's equation would give you the refractive index, and actually it not only gives you 1 but 2. Yeah? Yeah. So what it means is that for a given wave vector, an anisotropic crystal can only transmit 2 waves that are linearly polarized in one of 2 mutual orthogonal directions. Yeah? So one can prove that these 2 that the D fields corresponding to these 2 refractive indices, they are orthogonal to each other. Yeah? So it transmits only 2 polarizations. You could say, how bad? Well, but actually it's not so bad, because if you have any other polarization, you can still decompose in these 2 allowed polarizations, right? So all polarizations are allowed. You just need to decompose it into the 2 that come out of the Fresnel equations. Yeah, so that's written here. Okay, so next point is the index ellipsoid, also called the indicatrix. Now remember that we used this trick that went via the energy density of the electric field. Yeah, so WE is equal to 1/2 E times D. And what we got from that equation was actually, of course, a tensor equation. And if you look at it, then you see that it's actually the equation of an ellipsoid, as we said already, right? Now the energy density, so the energy density in some material that doesn't absorb would be a constant, right? So therefore we divide through this left side here, and we normalize it to the energy density, and then we get indeed the equation of an ellipsoid. Yeah, so here we still had the dielectric constants here, and here we have now the refractive indices. So you can think about the optical properties of an anisotropic medium as an ellipsoid. And depending on the direction in which you have your electric field, the refractive index is just is just proportional to the distance to the surface of this ellipsoid. Right? So I tried to show this here. So we have this ellipsoid here, and we have here the wave vector k. Right? This blue plane here, this is the plane perpendicular to this vector k, right? Something like this. And here we have the, this intersection here, this gives you the refractive indices, right? And so these two half axes, this is what comes out of Fresnel's equation, right? So you have now a pictorial representation of what we explained before. So now it depends on which kind of material you have. So for many crystals, for many symmetry classes of crystals, you have actually the case that two of these half axes are equal, right? And for some, actually, all of them are equal. Yeah, so all three are equal. But of course, there's also this most general case where they are different. So now, when this ellipsoid here would be an ellipsoid of revolution, then this vector here would be, say, parallel to the x direction, and the ellipsoid would be an ellipsoid of revolution. Then, of course, this cross section here of the ellipsoid would be a circle, right? Is this clear? And this would mean that the refractive index for both polarization directions is equal. Got it? Yeah? So if we would, once again, yeah, so assume that that this ellipsoid here is an ellipsoid of revolution, rotational symmetric around the x-axis. Right? Further, we assume that our wave propagates in the direction of this x-axis. Right? This means, because we have a transversal wave, this means that the electric field oscillates in this plane that is parallel to the y-z axis. Right? And the cross-section of this plane would be a circle, because we said that this ellipsoid is an ellipsoid of revolution. And this means that whichever polarization you take, you have the same index of refraction. Yeah? Then this anisotropic crystal actually behaves as if it would be just a piece of glass. Yeah? So there is no birefringence then. Right? Okay. Yeah, so these are the two indices of refraction, so these yellow lines. Now, let's look at the general case. And what we assume is, without loss of generality, that the half-axis in x direction is larger than the one in y direction, and the one in z direction is the smallest. Right? The one in z direction is the smallest. And again, yeah, so we take here the cross-section. But what I want to do now is to rotate. Yeah, so again, k is along the x direction initially, but now I want to rotate here in the xz plane. Right? Then you realize that nothing happens to the half-axis of this ellipse in y direction, whereas this one here, as I rotate k in the xz plane, whereas this one here, so nz gets larger and larger until when k is parallel to the z-axis, this half-axis becomes actually nx, so the largest. Yeah? So we move it from the smallest to the largest refractive index. Right? And at some angle here in between, it must be equal to ny, right? And then if this half-axis is as big as this one here, we have again the situation that if you shine light with a wave vector in this direction, that it doesn't depend on the polarization. So all polarizations deliver the same refractive index. In other words, and these these directions, they are called the optical axis. Yeah? Okay, so you have seen that a crystal that has an indicatrix that is rotationally symmetric has a single optical axis, and one that has the lowest possible symmetry has two optical axes, because of course if I move it in this direction, say by 25 degrees, and have the situation that the cross-section is a circle, then I can also move it in minus 25 degrees and would also have a circle as the cross-section. Right? It's quite easy to calculate the condition under which we have this. We find the optical axis. If we know, of course, the indices of refraction in the principal axis system. Okay, I guess this is that's it for today. Let me see. Yeah, so here you see the same thing actually. Yeah, so what I explained here, I've forgotten to show these pictures. Yeah, so once you go here in direction of the optical axis, then the cross-section is actually a circle. Good. Yeah, and with this we can define the ordinary and extraordinary direction for uniaxial crystals. This summarizes the so the phenomenon of birefringence. It was actually discovered quite early in history by Bartholin. Came from a family of several famous scientists. And others like Huygens tried then to explain the effect that he observed. Right? Here you see a picture that I found on Wikipedia of a Kalkspat. And here you find these two people who actually were the first to explain birefringence. So they discovered the nature of polarization, Fresnel and Arago. And I show here the Tour Eiffel, so the Eiffel Tower in Paris. Not just because they worked in Paris, but because you find their name here so here Arago, and I'm not sure where you would find Poisson next to him, right? And here Foucault, but I guess Fresnel is here, right? So once you're in Paris, take a piece of binoculars because it's pretty high up there, so that you can read the names. Yeah, the French, they know how to celebrate their heroes, and this here is one example. So next time we will look at induced birefringence. So we would use an isotropic material and apply a strong field. Actually not an isotropic. We would use a crystal and apply an electric field and change its bioreferentials. And many of the concepts that are developed there, you will find again in nonlinear optics. Yeah, so it's very worthwhile to look at the electro-optic effect or the Pockels effect. Yeah, with this I would like to thank you for your attention. I will stop the YouTube now, but we would continue with a discussion of organizational things. Thank you for your attention.